continuidade a essa batelada de aulas sobre biotecnologias, o professor Klaus, ele apresentou aspectos gerais e aspectos sobre o clima e a repercussão sobre o clima a partir da gestão de resíduos. Nessa aula agora ele vai entrar nas tecnologias em si, nas biotecnologias. Professor Fricke, Klaus, you can start.
Okay. So hello everybody. We do it at our university in this way that when we start with the lecture, we make a little repetition of the content of the last lesson. And so I will do it in this lecture also. So you remember the last lecture, you have known, for example, the structure formulas of photosynthesis, of aerobic and anaerobic processes. You need it, you have to learn it, because when we talk about biotechnologies, you must know these three formulas. Then we explain a little bit the carbon and the nitrogen cycle and the function of enzymes. You remember what was the main point of the enzymes? I hope. Enzymes are very important for degradation, but because enzyme consist of proteins, they don't accept temperature above more or less 55 degrees. So when you have to enhance the composting process, try to be below this temperature level. Then we learn something about the organic matter, about this different kind of materials inside the organic matter. And we learn that, for example, there are some components, for example, like lignin or other components, but particularly lignin like wood and so on, is not degradable by anaerobic bacteria. And aerobic bacteria, it means composting bacteria, are so-called omnipotent. That means all components formed by photosynthesis are degradable by composting process. The next point, we talk about raw materials for suitable composting and for fermentation. We learn that, for example, wooden components, humus components are not suitable for fermentation processes. Then we learn these different kind of stages of aerobic and anaerobic degradation. And later on, we learn the main point, the importance of water content and temperature. I think these are the most important parameters for processing both of these biological processes. Then we talk about collection systems. The main two collection systems, on one hand, you can do it by separate collection to produce a compost, or separate collection to collect bio-waste for producing compost or producing biogas, or you can do it from mixed waste compost. And the main parameter, the main quality parameter is, or was in the past, the heavy metal content, but nowadays also the content of plastics because of marine litter, because of this growing very important problem of marine litter. And at the end, this was a special lecture. We know something about the impact of these processes for climate change. And we learn that the best option is the combination of anaerobic composting, anaerobic digestion and aerobic composting. But very important, we will learn today, it doesn't mean that you have to start immediately with this two-step treatment. You will learn that maybe it could make sense. Start in the first year with the composting process, learn about these processes, learn about a lot about the material, and later on integrate the anaerobic process, the fermentation. But I think at the end you will understand this point. So we start at first with technologies and with processes from composting. So where we can use these biological processes, this was on one hand to produce compost, on the second hand to stabilize organic materials for landfill because of the reduction of organic matter as the basis of methane emission. And we can use this composting process also for this aerobic drying, I will explain a little bit later, to produce biofuels. That means to dry biomass to lift up the energy content. So at first, what was the goal of composting? We described it as achieve a special degradation rate. You can mean it also the maturity degree, or we call it in Germany Rottegrad. But maybe in English, I think it is a better this explanation. It's the level of maturity. And the higher the maturity is, the higher is the better is this material all over the use in agriculture and particularly in gardening area. So that means if you want to have a compost product with this maturity degree of 5, you need a degradation of organic matter between 40 and 70%. This compost you can use in all areas of gardening and agriculture. And on the other hand, if you want to achieve a high content of organic matter and also sanitation, then it is absolutely not necessary to have a very high degradation of organic matter. Then it is enough to have a degradation of 10 to 20%. So the amount or the level of degradation depend on the use of the compost. And if you want to use the compost in the agriculture area, normally it is enough to produce a so-called fresh compost. That means maturity degree of 2 and a degradation rate between 10 and 20%. So you can save a lot of energy for this composting process. And the main value, the main component or the main value of the compost in this case is the organic matter and a little bit the fertilizers. How to measure this levels, this different kind of levels of maturity degree? You fill in a so-called dewar vessel with a special water content, and then you wait and then you measure the temperature inside this vessel. And when the temperature is above 60 degrees centigrade, then it is a raw material. Sorry, my God. It is a raw material. It's not a straw material. Please corrigate. I don't know how it's come into this table. And when the temperature achieve below 30 centigrades, then it is a finished compost, so with a very high degradation of organic matter. So this is the main requirement for this different kind of maturity degrees which you have to achieve. And again, background is where you want to apply these compost products. So short, you can say, if you want to use this in gardening area, you need a very high level of maturity degree. And if you want to use it in the agriculture, then maturity level of 2 is absolutely enough. So let's come to the next point. How we can achieve this different kind of degradation rates. And so we have here some process control parameters. The first and most important parameter is the oxygen supply. So you need sufficient oxygen supply. You need also sufficient temperature. That means temperature below this 55 to 58. But also you need a sufficient water content in your raw material. There are some other points. I think at the end we will talk a little bit about it, but all these other parameters are not so important. The most important are these three: oxygen supply, water supply, or sufficient water content and sufficient temperature level. So we start with oxygen supply. At first, I want to give you a formula, and in the slides you find a lot of formulas, but only this one formula I will show you and I will explain as an example. So, oxygen supply. What is the amount of oxygen demand for degradation of 1 gram ODM, organic dry matter? This is the number of around 2 grams. That means you need 2 grams oxygen to degrade 1 gram of organic matter. It's depending a little bit about dependent to the composition of the organic matter. So it could be a little bit more or it could be a little bit less, but in average, you need around 2 grams. And for your calculation, it's absolutely okay. And you don't need special numbers about oxygen demand. So what do you need also? Yet on the left side, you see at first the amount of air requirement. How much cubic meters you need. So at first you have the organic matter, the degradation, the percentage of organic degradation rate you want to achieve. You have the U2 stoichiometric utilization degree that for the degradation. Again, you have to divide everything by the density of air and the oxygen content of air. And here you see the numbers. For example, the density of air, of normal air, is 1.2 kilograms per cubic meters, and the oxygen content of air is 20.9%. And let's go through this formula. At first, we say our model compost has 65% of water content, and that means 35% of dry matter. So that means 350 kilograms dry matter per ton raw material. But this dry matter has 66% of organic dry matter, and 66% of 350 kilograms are 231 kilogram of degraded organic matter per ton raw material or per ton bio-waste. Next step. We have these 231 kilograms and we say we want to degrade it by 60% because we want to achieve by the composting process a maturity degree of 5. So you need a very intensive degradation rate by around 60%, and this means we have 139 kilograms of organic matter degraded. And then we have the next step, 2 kilograms oxygen by kilogram degraded material is around 278 kilograms. So it's a very simple system. We multiplied 139 with the 2 kilograms of organic matter, and so as a result we need for the composting process of 1 ton of bio-waste 278 kilograms of oxygen. And then we have the next steps. We have to add the amount of air with the density and with the oxygen content. And at the end, we say we have 1 cubic meter per 1,100 cubic meter per ton. But now we have a little problem. This is the amount of air you have to add in the composting process when the microorganisms catch every oxygen molecule, but they are not able to do it. So we say from the added air in the compost pile, it's only possible to achieve a 25% taking out of oxygen. So you have to add factor 4 of air so that you can guarantee that the microorganism gets the total amount of oxygen. And so we need not 1,000, we need 4,500. Okay, I hope it was understandable. And for this kind of calculation, we have a lot of very simple calculation to find out the amount of energy we have to take out. We have to put it in water. We have to calculate the water amount, the loss of water, and. So, but I think this is enough for an example for calculation. So next point is, what can we do when we are working on a compost facility? What can we do to make sure that we every time have enough oxygen in our compost windrow or in our compost pile? So, at first, it's a very important part, the ratio of windrow surface to volume. Why this is so important? I will explain a little bit later by some pictures. Then the next point, air-filled pore volume. The main point is that we have two aspects in our compost pile. We have pore volume, and about this open, not filled pore volume, we can have, for example, the flow of air through these open pore volumes. But when you have on the other side very, very poor open pore volume cause of very slow amount of pore volume, and on the other hand of filled pore volume with water. Both is bad for this oxygen supply. So the fourth opportunity is active and passive aeration, and the last point is windrow setting, turning, and time, the timing and frequency. So I will give you some ideas about these 4 options to enhance the the oxygen supply. So at first you see this surface volume ratio, and you see here we have a triangle windrow, we have trapezoid windrows, and we have so-called table windrows. And at the end you see more or less the higher the windrows, the lower is the surface volume to the surface to the volume ratio. So the higher the surface to volume ratio is, the higher is the opportunities for the air migrating inside the windrow. And this passive migrating inside the windrow is the precondition for more or less the passive aeration. And when we have a very small surface to a very huge volume, then normally it is impossible that oxygen or air migrated inside the windrow. And that means, for example, very huge huge windrows with wide base and wide top and high, very huge high, then you have a huge problem of oxygen supply by passive aeration. And that means all these huge windrows, and particularly windrows with in the form of table windrow, you need active aeration. On the other hand, that means when you have very small windrows, when you have enough space on your compost facility, use or work with small windrows, and then it is not necessary that you aerate these compost piles. But we came now to this windrow setting and turning. What is important for setting and also turning? Setting, it's very important that you have the compost pile with lowest possible bulk density. That means, have you a very low density, that means you have a lot of air pore volume in your compost pile. This is the precondition that you have oxygen inside your windrow, but also it's possible that the oxygen migrate inside the windrow. And after a short time, the microorganism takes this oxygen and use it for the degradation process. And normally after 3, 4, 5 days, you have no oxygen inside your pile, because the total amount of oxygen is used by the microorganism, by the consumers, you can say it also. So that is the reason that you turn your compost pile. Some do it after 3 days, some do it first time after 2 weeks. This depends on this different regime you have on your compost facility. With these technologies, I started my career in this area of composting in 1983. And in this time, I learned to drive trucks and. So this is a very simple system every farmer could use, because they have this kind of turning devices. But the modern composting systems use so-called automatic turning systems. They are driving with a special turning system through the compost pile and mixed with a special roller for fluffing or losing the material behind this machine, and also mixing it. For example, mixing the outside material in the inside material. This is again a precondition for sanitation. Very important part. Sanitation. The sanitation in the composting process takes place by using the high temperature in the compost pile, and you must turn it one time, and you must mix the outside cold area of the compost pile, mix it inside. So at the end, after the first mixing process and after normally totally 14 days, all the material is sanitized. And here you see some example how it works. This is a very well-known company called Bacchus. They have special turning machines. They are moving over this compost pile, and normally they awarded the material, so they irrigate the material that they can enhance also the water content. This is another way of turning system. This is a turning system you can build, so-called table windrows. This again a very, very simple turning machine, but using it with aggregates from the agriculture. And here again you see this another company. You see this turning machine and you see the dust. This is nothing else than water. Because when you turn it and you have temperature about 55, 60, 65 degrees, then water will evaporate, and so you see the water steam. These are some machines more or less for small composting facilities up to 10,000, 20,000 annual capacity. And I show you now some machines we use in Europe and some we use also South America. These are so-called table composting machine, and they turn with this wheel, they turn the compost, they take it on the conveyor belt and replace it again some meters behind it. This is a totally automatically turning system, but I must say it's a little bit historical technology. The modern technology, at the moment, they use more the so-called tunnel systems. I will show you a little bit later. So this is a German technology, but we have it also in Spain. We have some in Dutch and in End. And this is, I think, a mixture of Italian and Spanish systems called Biomax. It's a special turning system. And you see here, there are drilling components. They take out the raw material, the material, you see it here again, and then they take it out from the primary windrows and replace it 1 meter or 2 meters behind, mix it end and end. So this kind of technology we have, for example, in Argentina, in Buenos Aires. They have built it there, I think, 4 years ago. So also a table windrow technology. And for huge facility, more and more important came this technology in so-called totally encapsulated tunnels. And in these tunnels, we have, for example, an aeration system, and they all have aeration systems, and some have also this filling system, this automatically filling system, or they use four-wheel drives. I would say all new compost facilities are built, huger one, 60 to 70% will use more or less such kind of tunnels. So the absolutely precondition is you can enhance the aeration very exactly, and you have a very good opportunity for catch the air for the air treatment. So next step, how to organize and how to make sure that you have sufficient oxygen supply is the active aeration. So this is a very simple system. You have a van, you have a tube, a drainage tube with some holes inside, and you blow in the air for the microorganism to have enough oxygen over the whole time in the more or less in the whole area of the compost pile. And here you see it more by drawing it. In the middle, you have, for example, your pile from which oxygen will be pressed inside the compost pile. So this is a typical pressing system. You press air inside the compost pile. On the other hand, there are systems, they suck it out. So let's discuss about sucking system, blowing system. This is a special philosophy of different companies. Here's also a very simple system. Here you see more or less the battery of vans, and here you see, for example, this in the ground integrated system for bringing the air inside the compost pile. Sometimes they use, for example, organic components to cover this material to make sure that we have a good distribution of oxygen. And when we are using the systems of tunnels, then, for example, you have an aeration floor, and from this aeration floor, you blow air inside the compost material, and so make sure that they have in every area of the compost pile, in every area, you have your sufficient oxygen in the compost pile. Here again, this, for example, this tunnel with the openings in the ground for the aeration slots. This is, for example, the ground of a windrow table, also with the aerating slots on the ground. So this was at first, make sure sufficient oxygen supply. Next step is the temperature. How to enhance the temperature to make sure that the temperature is not, we say it in Germany, is not running away. That means that you make sure that we below 60 degrees. When you don't manage it in huge compost piles, that means with a small surface volume ratio, then you could have temperature up to 90 degrees. Then you kill all important microorganisms. You destroy the proteins. And normally, when you have this situation, you need some months to reactivate this compost material. It's crazy. So, but at the end, why we have this problem with the temperature is 2 points. If we degrade 1 kilogram of oxygen, we set free around 20 kilojoule of heat. So, on the other hand, we have a heat production, but additionally, we have a low thermal conductivity. And at the end, these both factors will initiate a so-called self-heating in the windrow. Self-heating in the windrow. And this is a picture, as an idealized picture for the compost temperature. At the beginning, you have an increasing after 1 or 2 days, you achieve around 60 degrees. And at the end, the temperature decrease, and at the end, we are on the level of the outside temperature. But what is important? So, at first, we have the organic matter, which is easily degradable. So, this is the background that in the first 2 weeks, we have a very high degree of organic matter, means a very high amount of energy setting free. And later on, you have the not so easily degradable components, and the amount of heat produced will decrease. And this is a very typical temperature or an idealized temperature for composting processes. And here you see again this question, high windrow volume, low windrow surface. So when you have the problem that the conductivity is very bad and you have a very small surface but a very high volume, that means you have a very huge amount of material producing energy but a very small surface to set the energy free. That means high windrow volume to low windrow surface, we have much more longer high level temperature than small windrow or low windrow volume and high windrow surface. So these are a lot of components you have to know. And again, this is a repetition. Think about the aim must be to reduce the temperature that you are lower than, say it easily, lower than 60 degrees, cause of the protein denaturation. How we can control the temperature? Again, this windrow geometry, I have mentioned it. Air-filled volume to discharge evaporated water. What is the evaporation of water and what does it happen, or where is the combination? What is the effect to the temperature? It's very easy. When you have high temperature, when you have water, then you evaporate the water. and by evaporating, you achieve a cooling effect. But this evaporation can happen, and it's only possible if you have enough pore volume for water and also pore volume for steam. And the cooling effect is the evaporation effect. It's the most important in big facilities. Turning frequency, again, when you turn your windrow, you set free a lot of heat. You have seen it on the picture. And again, passive or active aeration. So, again, I think this is very important. Air acts as a transport medium and water as an energy carrier. So this is so important that you have an airstream flow, and in this airstream you must have water, the steam, and the steam takes out the energy. This is the composting process. So I will show you this at a little picture. For example, if you want to take out the energy out of the compost pile, you blow in cold air. And cold air means on the other side with 30 degrees, as an example, the air can carry more or less 30 grams of water per cubic meter air. Then we heat up the air. Then we have the temperature of air of 50 degrees. But hot air can carry much more water in the cubic meter. It's more or less factor 3. So that means you take the air, takes the water and carry it out. And by this process, you take out the energy. But on the other side, how can we use this process? What do you think? We're taking out the air by heating up the air, lifting up the capacity of carrying, and taking out the energy mainly produced by the evaporation. So this process you can use also for aerobic drying. That means you can dry a raw material, an organic raw material, to reduce the water content on the one side, and on the other side you lift up the energy content, the heating value, the lower heating value. So this is nothing else as, on one hand, a cooling system, but on the other side, a heating system. But when you see all this combination of cooling, of heating, and an end, you see at the end you need a lot of water. By this intensive process, you need a lot of water you have to add in the compost process. And here again, the water hold capacity. The capacity rise by rising temperature. Here you see the water steam capacity, and here you see the dependence to the temperature. It's a very simple physical process. And now, to understand a little bit more about the water, I will come to the last point of water. You see here, I would say it's a bio-waste. It's a mixed bio-waste. You see, you have your organic matters, you have the water-filled pore volume, and you see here the air-filled pore volume. And only when you have air-filled pore volume, then a passive aeration is possible. This is so important. So at the end, sometimes you need structure material to lift up the amount of pore volume. I will show you at the end some examples for structure material. And the problem is, in this, with this air pore volume, very close relation between moisture and aeration. Both needs pore volume, which can only be filled with free water and air. So this is a little bit the fighting of water content and oxygen supply. So you must find an optimum between these two requirements. Here you see a dewatering from agriculture area, or you see a dewatering in a turning system. You see here, for example, a hose wheel, and for water, this is this wheel for water supply. You supply the water over the whole surface of the windrow. And now the question, why you do it before and not after the turning process? Very simple. You add the water before because after this water adding action, you have, after this process, the turning system, the turning drum, so that you mix the water homogeneous in the compost material. This is the only reason why you take it before. Otherwise, you have the water outside on the surface, and after a short time, it will be burned out more or less by the sun. And you have on the surface high water content and inside low, and this is shit. And again, when we talk about this system, the tunnel composting system, you have on the top an irrigation area, and so you can use processed water or other water to bring in, to lift up the water content or to hold the water in the required area. When you look at, again, to the aeration, the higher the intensity of aeration, the higher is the loss of water, and so consequently, the higher is the need of additional water. So again, to the structure, I show you this material, this picture again, because I want to give you now the last point of the composting area. What's about structure material? When we have only kitchen waste, then the structure, that means the air pore volume is very low. And when you have only kitchen waste, it's very problematically to realize a sufficient composting process. So normally you have to add structure materials. That means structure materials, I will show you here. For example, chopped wood, tree and bush cuttings, you see here. When you mix it inside, you lift up, you reduce at first the density and you lift up the air pore volume. You can use wood fibers, you can use bark, coconut fibers, for example, for the Brazilian and for the Asians, chopped bar and walnut, chopped straw. There are a lot of components depending on the area the composting facility is placed. So this is a very simple but very important part for managing the right structure, and this is the precondition for oxygen supply and water content. So at the end of the composting process, you see here some flows. We have at the beginning the entrance area where you control the material, that they bring you not wrong components, for example, or components with high amount of impurities. So you can control the material, and for example, you can sort it out manual or by special treatment facilities. Then you have the pre-treatment before the composting process. You have here at the end the composting process, the refining, and the storage. And the impurities mostly plastics you bring lately to the energy recovery. And the main reduction of amount of mass you have on one hand by the rotting loss, that means carbon dioxide and water. You remember the structure, the formula of aerobic degradation. The result, the final product is carbon dioxide of water. And so you can have between 20% or you can have 70%, depending on the intensity of degradation. And the amount of impurities is depending on the area. For example, we have in Germany some areas where we must say, you remember the pictures I show you about problematically social areas. Normally, the amount of impurity is much more higher than in the countryside. So, but these are materials we have in Germany, we must bring into thermal treatment or energy recovery. This is a very simple system, for example, like we use it on very small facilities. And normally, it's in bigger facilities, we also make in the first pre-treatment step a manual sorting. That means the people sort out plastics and out of the bio-waste. The more modern technology use also different kind of automatically detection systems and blowing out this kind or taking robots to take out this material. We have a new law, and I think on the long-term view, we will have it in all countries in Europe, and maybe I think also maybe in Brazil and other countries. You remember that I mentioned that we have nearby climate change, another huge problem, and rising huge problem is this marine litter. 80% of marine litter entering from the countryside. And one point could be also compost. When you don't clean it exactly, and I mentioned some numbers of compost pieces in 1 kilogram dry matter from 50 to 800. And the consequences, you have to take it out before the composting process, before the shredding process, because otherwise you don't have the chance to get it out. And so we have a new law. It is, I think we will have it at the end of this year, where it's required that 90% of the impurities have to take out before the composting process. So very, very important as one part of fighting against marine litter. And now you see some more intensive pre-treatment before the composting process. We have again green waste and bio waste. We have the entrance area to control it. And for example, the green waste is shredded and then bring it in a homogenization system. And the material was separated by ferromagnetic components, and we have a screening step by 80 millimeters. So the coarse grain of the bio-waste, bigger than 80 millimeters, is transported to a sorting station for manual sorting. Why bigger 80 millimeters? It's very simple. 80 to 9% of all impurities are in the coarse grain, in the grain size bigger than 80 millimeters. And so you can concentrate the impurities in this special fraction. Some bring it directly, the entire fraction, to the energy recovery, and other separate these organic components and bring it back in the composting process. So there are different ways for this pre-treatment. And after the compost process, maybe this is the picture we like to see, and this is the goal of, for example, the processing after the composting, or also refining, named refining. separation of impurities, adjustment of the required grain fraction. For example, in Europe, we have a required grain fraction by smaller 20 millimeters, smaller 50 millimeters, and some also smaller 8 millimeters. Product refinement. There are some areas they refine the material with adding some fertilizers and. And some are packing the material because packet compost, you can earn a lot of money. You can take much more higher prices, higher revenues, but it's not so easy to do it and find and to build up or to create markets for these products. And the screen residues after it also can be transported to the, in your case, to the landfill. And in Germany or in Europe, you have to bring it to the thermal treatment. But also these screen residues around 30%. And so there are more and more technologies. For example, they refine the screen residues. So pre-treatment, in this case, composting, screening by this 8 or 15 or 25 millimeters. You have the overflow, you can transport to the energy recovery, and at the end, they have your final product, compost. But you can do a lot, you can do more, because the thermal treatment is very expensive. And so some of the compost operators or compost facilities owners integrate, for example, treatment of this material, of the overscreen. So again, we have the screen and combine the screen, bring a screen in a combination with a wind shifting system. So we screen by 8 or 50 millimeters, and we clean the overflow, for example, with the wind shifting system. And so this material is more or less free of foils. And so we can use it again, we can turn it in a cycle in the compost process. And with this point, you can reduce the amount of materials bringing to energy recovery. And a second step, also possible, it's a so-called a hard material separation. You can take out glass and stones. This you can bring to landfills. So is a widespread area of pre-treatment systems, composting systems, and refining systems. It's depending a little bit on the size of the capacity of the compost facility. It depends also on the market situation, surround the compost situation, and. And at the end, you have your compost in boxes and piles and also in sacks. Last point, for example, a normal compost process with a degradation of around 55% of organic matter. We have a loss of carbon dioxide and water by 50%, 10% for energy recovery, and around 40% of compost. For example, when you have a material, a very wet material, not with 60 or 55% of water, it could be that you have materials about 70%. Then the amount of degradation of the composting loss, it's about 60%, 65%. So the balance of the mass balance is dependent on one hand, how to treat, how to pre-treat, and how to refine the material. Also dependent on the degradation rate, and very, very important is the quality of the raw material, particularly the water content. So second part from today, we talk about fermentation. Sorry, it is a fault. It doesn't mean composting. It means fermentation. And again, the first point, you remember that what is fermentation? You know the structure formula and you know the different components which are available for anaerobic microorganisms. And here's some fundamental information about this different kind of organic matter according to the amount of biogas. Carbohydrates, proteins, and fats. These are the most important organic components. And you see, you don't have to learn it exactly, but you have to see this different kind of organics have different kind of the amount of gas you can gain by anaerobic digestion. But not only the amount is important, the energy of the biogas, and this is the main value, is not the amount of gas, is only the content of methane. And you see proteins, for example, have a very high amount, and fats too. Carbohydrates, not so much. And at the end, the calorific value differ dependent on the concentration of the part of methane. This is very important. And so this will explain you something about this different kind of waste. So at first, what kind of waste we can have for anaerobic digestion, for example, separated collective bio-waste, industrial organic waste, but also the organic fraction of a mixed waste. This fraction is in the fine grain, more or less smaller, 80 millimeters. And now something about the amount of gas. When we have a bio-waste mix of kitchen and garden waste, we have around 75 to 136 cubic meters. But when you have only kitchen waste, the amount of proteins and fats is much more higher. So it's up to more or less the double of biogas. That means for anaerobic digestion, kitchen waste has a much more higher efficiency. And also the organic matter from the municipal solid waste, because the main content of the organic matter are origin from kitchen. And the Brazilian one, I would say it's a little bit higher than the one in Germany, because the amount of organic matter is much more higher than in the German mixed waste. This is something to do with small amount of packages and also cause of separate collection. So this is the background for anaerobic digestion to gain biogas as a renewable energy. And now we came to the structure, the systematization of processes. We have 1, 2, 3, 4 different kinds of, in principle, different technologies or different processes. At first, we have mesophilic and thermophilic temperature. All these technologies you see here can work with mesophilic or thermophilic temperature in the anaerobic degradation process. And you see this is the main part. The mesophilic process is between 30 and 36 temperature, and the thermophilic between 50 and 60. But meanwhile, you find such a lot of different numbers you can find here, 32 to 30, 39, and here you also find starting by 45 to 60 degrees. So these are the main temperature area you find in the literature. So what is important? The performance of degradation is very bad when you have very low temperature, smaller than 25 degrees. This psychophilic process you use only when you have, for example, huge volumes of fermenter and you don't know what to do with it. So then the time is not the problem. But in the practical area, we have only mesophilic or thermophilic temperature and processes. And what is very clear, the performance of degradation by mesophilic process is not so high like in thermophilic process. But on the other side, the process stability is higher in the mesophilic than in the thermophilic process. This is depending from the different kind of microorganism you have. So the community of microorganisms in the mesophilic area is much more various than in the thermophilic one. But the tendency we see in Europe and in Germany is to operate with thermophilic processes, thermophilic temperature, because the amount of gas is around 15% higher than by mesophilic temperature. And here you see again, for example, these are lab analyses where you can see this development of temperature, mesophilic area, and here the thermophilic area. And you have it also for the first steps in the composting process, as also in the area of methanization. So again, you can use this thermophilic and mesophilic processes with all technologies for anaerobic digestion we have on the market. And there are a lot of options to bring in the heat. Please look later on when you get the slides. Here you see the different options how to bring in the temperature. You have to heat it up. You have to heat the raw material in the fermenter, because the energy you set free by degradation is, instead of 36 ATP, only 2. And this 2 ATP is not enough for self-heating. Why we have such a low amount of energy by degradation? Where is the energy? Where is the energy gone? It's very simple. The energy is in the methane, so the balance is the same. But because you only have such small amount of heat, you have to add heat, and normally you use it by taking the CHP. I will explain you later. So there are another system for anaerobic digestion. At first we have mesophilic or thermophilic, and now they are totally different technologies, the wet ones and the dry ones. Wet and dry means with high and very high water content and with more or less low water content. So again, we have different kind of technologies. We have, for example, water contents from 1 to 15%. And the degradation rate by these wet processes is very high, and in the same, more or less on the same level like the dry processes. We make a differentiation between continuous processes and discontinuous one. I will explain later. So the fermentation volume for wet process, sure, is very high because you add water, you add a lot of water, and so you lift up the volume of your raw material. And so for this huge volume, you need huge volume of fermenter. Not so much like in the dry technologies. And another point is very important, and it's negative. The energy demand of the technical equipment is by these wet processes very high, because at first you have to add water, and at the end you have to dewater the material. So 15 to 30% of all energy demand comes from the water area, particularly from the dewatering area. So the differentiation I will explain later. So how to bring in the water? You use special kind of pulpers. This is a machine originated from the paper industry. So you have a very huge volume with water, you bring it in turbulences, and then you take the water and use it later and bring it later into the fermentation. Some systems use it as a steady, as a continuous one, and some use it as a discontinuous one. So the discontinuous one, they stop this turning process, this bringing in rotation, then they stop it. Then we have the swimming situation, this floating material like plastics you find on the surface, and the heavy components like metals and stones and glass you can take out on the ground of this fermentation. So a very simple system, floating and sinking or sedimentation, separation, and taking out this material. Or you make it continuously one, and then you have to bring it in a so-called wet screening step. At the end, you see very intensive amount, very huge amount of technical equipment and huge amount of energy. And at the end, this will have consequences I will show you later. And the third one is the multi-stage and one-stage technology. So the one-stage technology, only wet processes technologies are suitable for two-stage processes. And this two-stage process differentiate made by some suppliers install a short aerobic hydrolysis before the actual fermentation process, and so they bring in the heat. But the main point is that we have, when we focus on these 4 steps of degradation, they have special environment requirements. And yes, you will see here, the hydrolysis and acidification, these are the first 2 degradation steps. They differ particularly in the area of pH value, and also in the redox and. So the idea behind these 2-stage steps is optimizing or having optimal degradation condition for these these steps and the methanization area. And at the end, it is said that the total amount of gas you can gain in a shorter time. This is right, but in principle it is right. So that means a 2-step technology can realize the anaerobic degradation in a shorter time, and some said in totally the amount of gas is higher than to have the degradation in one fermenter. But I will show you at the end results. 1-stage process, 2-stage processes. So process control of the specific degradation phase. 1-stage and 2-stage, it's the intensity, the amount of process control. Degradation rate, we have in a 2-stage process, it's a little bit higher. Process stability, sure. When you can arrange optimal environmental condition for the bacteria in the different kind of degradation stages, then you have a higher stability. But the main point, and this I think will be at the end, will clarify the development of 1-stage or 2-stage technologies. This is the technical expenditure. This technical expenditure is much more higher by 2-stage processes compared to 1-stage process. And at the end, that means much more expensive. So last point about these processes, you have to learn what is a facultative anaerobic bacteria and what is an obligate anaerobic bacteria. So, facultative air bacteria, these are organisms. They can switch from aerobic respiration in anaerobic. You can use the first two steps of anaerobic degradation. So these can be facultative bacteria, so they can work with oxygen and also without. So this is the background that some anaerobic digestion facilities has as a first step an aerobic step to prepare the raw material for the methanogenization. And only in the area of acidification and of the methanogenization, there you have obligate bacteria. They can only live without oxygen. This is a very important part because you very often seen in the practical area that we have and so-called aerobic pre-treatment before the main anaerobic process of acidification and methanogenization. Here, for example, some process control parameters. I don't want to talk in detail about it, but you know, the most important thing is the gas rate. You have to know what is the formation rate of gas. This is a very important parameter. Temperature also and pH value. There are a lot of other things. Would be we have to go more in detail to explain everything, but this time we don't have. So, but now the main results. What could I recommend? What kind of technology we have to take? And according to wet and to dry technologies. So you have to know before we start the anaerobic digestion with wet technologies. We start with dry technologies 30 years ago. In the 80s, we have the first experience with dry technology in France, in Switzerland, and later in Germany. So we start in the area of bio-waste fermentation with wet technologies, and the wet are the red numbers. And you see they stop more or less in the year 2006, and they don't build relevant facilities with wet technology. And the main reason is they don't produce, or with wet technology, you don't produce more biogas than in the dry technology, but you have much more effort to realize this process. So at the end, in the energy balance, the dry technologies have better balances than wet technologies. And the wet technology are much more complicated. So you have much more problems of process problems, for example, by sedimentation, by floating layers, and the third, and I think this is the main reason, they are much more expensive. So the most companies in Germany, they don't offer wet technologies. And now I have to say, but, it's a very big but. All what I explain you is right for more or less dry materials, like bio-waste, like remaining, like mixed waste. We have in Germany 10,000 facilities in the entire area of agriculture, wastewater, and 90% are wet technologies because the raw materials are wet. It makes no sense to take dry technology, then you have to dewater the material before. This is nonsense. So what I say here, according to dry and wet technology, is only for dry technology, for dry raw materials like bio-waste or like the organic fraction from mixed waste. For example, if you have sewage sludge, sure, you take wet technologies. Or when you have this different kind of manure from agriculture, you take wet technologies. Or when you have special residues from the industry, from the food industry, you have to take wet technologies. Okay, look at this mass balance and this flow sheet. You can see it's much more complicated when comparing to composting. Look at it when you are at home. I don't want to explain it, but I think it is self-talking or self-reading, so it's not necessary to explain everything. This is a typical one of the first dry technology called Compogas. It's developed in Switzerland. Now the owner is a Japanese company. It is a dry, continuously technology, and now I try to explain what does it mean continuously. Continuously means feeding and taking out. Feeding and discharge is continuously first in and first out. So the material is moving continuously through this reactor. And in this reactor, we have a mixing device. This is not a transporting device. It's only a mixing device for releasing the biogas. And on the top of these fermenters, you have this so-called gas dome, and there the gas is, you collect it and then you pump it out. And the transport moving is by pressing in the material and suck it out by vacuum pumps. And there are a lot of opportunities to bring the heat inside. You remember this slide I showed you some minutes ago. Another situation is also an horizontal fermentation. Oh, no, I don't want to show it because it's too long. It's only bad music in the background, but you can see later at home this movie. The same technology, another company, they don't have a mixing axe on this area. They have 4 mixing wheels in another position. When you say where is the biggest difference and why they make it different, it's so crazy. The inventors of both technology in former times was one group, and later on the group fight against, and so they have to develop a new one, and so they have to change something to have an own patent. Here you see the mixing devices inside these fermenters. We have also other fermenters, kind of fermenters and these vertically fermenters from the company Dranko. One of the most successful companies worldwide in building of fermenters. And now we came to another part, this continuously one and discontinuously one. So this looks like this tunnel composting. Yes, they are very similar to it. We have the process. We open the door, putting in, filling these so-called tunnels with raw material, closing the door, and then takes place the process in a time of 21 days. And this means discontinuously one, because you don't put it in and take it in the same side, taking the treated material out. You put it in, you have it as a batch system, and after 40 days, you open the door again and then you put it out. But what happened now inside this process? And inside this process, we have 3 steps. At first, you aerate it. You remember obligate and facultative microorganism. So they start with an aerobic process for 1 or 2 days. Then you lift up the temperature in this area, and so you have the first steps on the aerobic way. Then you stop the aeration and start with percolation. Percolation means this is processed water moving through this raw material, and from this percolation we produced the gas. We have so-called 2 areas of gas production. This is a percolate tank and also in this tunnel. And after 20 days or after 18 days, you start again the aeration. You stabilize the process, you stabilize, and you want to kill all bacteria, all obligate bacteria, and so you have an aerobic process, and the methane production came to an end. And when the methane production has to become to an end, then it is allowed to open this box and take out the raw material. This is a very simple process. So, and it's more or less at the moment a very successful technology in Europe, and it's from the amount of investment a very good technology, but this process produces not so much biogas than the continuous technologies. And it is very simple. But when you see batch system, at first aeration, second percolation, then starts the gas production, and at the end, after 20 days, the gas production reduced. That means you must have in minimum 4 fermenters, so that fermenter 1, fermenter 2, fermenter 3, fermenter 4, that you have a level of biogas production. If you have only 1, then you have this development of gas production and gas setting free, and it's impossible to drive a CHP with this kind of gas. So you must have a more or less same level of gas production. And at the end, a technology, the wet technology with 1 and 2 steps. I don't want to explain it in detail. What you see, at first you need the pulper to bring it in a liquid suspense. Then you have to take out the sand. It will work more or less very good. And then you have your fermenter. But what is very important, this suspense must be more or less free of sand. Otherwise, you have huge problems with sedimentation on the ground. And this was a killing argument in Germany for using this technology for the treatment of mixed waste. All 5 facilities we have built, they are all closed, and more or less all with the same problem. That means with sedimentation and sometimes also with floating layers, where we have plastics, fine plastics, and they're creating these floating layers. And this 2-stage, we have at first the hydrolyzed reactor, and as a second, we take this material after hydrolyzation, you take it in the methane reactor. So very complicated, a very huge offer, and so not a technology for dry waste materials. So some information about the amount of water, because the amount of water in Germany, it's a huge problem. In Brazil, not. Why I say it. So we have wet technology. After the process, we have an amount of water after dewatering about 280 to 500 liters per kilogram per ton, dry continuously 1 and dry discontinuously 1. So we have a lot of water you have to store. And what we can use this water, sure, we can use it in the agriculture. But in Germany, we have a huge problem because in this time where we have no plant growing, it is not allowed to bring in this water on agriculture area cause of saving groundwater. We don't want this material influencing the groundwater, particularly by nitrogen components. And so in Germany, it's necessary that you store this water about 9 months. And this is very, very expensive. So this problem you don't have, I think, in this way in Brazil, where you don't have any strong winter. And so you can use this water all over the year. And so you don't need no huge storing capacity. So after all anaerobic processes, you have normally an aerobic stabilization. That means you change from anaerobic to aerobic situation. Main point is that you lift up temperature again for sanitation, but also reduce methane emission. And the problem of the anaerobic digestion is also, we'll see it next week, that we have really high methane emission from fermentation processes, particularly after the process of particularly after the anaerobic process. So another step is sanitation or hygienization. On one hand, if you have a thermophilic process, the material is sanitized because of the temperature above 55 degrees over 14 days. If you have the mesophilic technologies, you need a post-sanitation in the composting process, or you have to do it in a special tank I will show you later. Reaching the desired degree of rotting or maturity degrees, and you have to reduce the water content to store it or to package it. These are the main goals or targets by the post-composting process. And here are some numbers you can read it later. Biogas production. Here you see at the end the amount of gas. Please have you in your mind. We have to make the differentiation. Biogas quantities in the fermenter input means not biogas production by the plant input. Normally 70% to 80% of the raw material will entering in the anaerobic digestion, and 20%, 30% are entering direct in the composting process because it's wood and. So you have to make this differentiation. So we see all numbers. I don't want to explain this different kind of numbers, but generally you can say the wet technologies and the dry continuous technologies are more or less on the same high level, and the dry discontinuous one have lower amount of biogas, and in general all thermophilic processes have higher gas production rates. What can we do with the gas? So there are a lot of systems we can use, mainly for all anaerobic digestion facilities use CHPs, that means motors with a generator, and then you produce the heat you need for the process and the electricity. There are also fuel cells possible. There are different kind of fuels you can do, for example, for trucks and then, but this higher level, this so-called methane gas, you can use only when you have a very high capacity, so that you can integrate a gas treatment. That means a concentration to lift up the concentration of methane above 90%. The main practical situation or the most used gas utilization technology is the so-called CHP. And you see here some performance dependence on the size. Normally, we have in Germany a size of 38%, from the produced energy is electricity and 52% is heat. And normally you need 1/3 of the produced heat for the own process. And it is very important that you find options to use the heat on your facility. And when you see now the net energy, then you will see that the continuously dry one have the best net energy yield according to this discontinuously ones, but also according to the wet technologies. And the consequences, why we need very complex, very complicated systems and very high amount of investment. Why shall we do it when we don't get more gas in net, when we can use cheaper technologies and technologies which are much more easier to operate? And this is the reason now you can understand a little bit better why since 10 years we don't build wet technologies in Germany for these two kind of raw materials. Again, you see here the flow chart of this different kind of these masses. We have on one hand the biogas use. It's normally 13% of the raw material. We have also liquid fertilizers, and we have composting. So at the end, the amount of composting raw material is around 37%, but it could be 25 to 40, depending also on the liquid fertilizers. For example, in Brazil, it's maybe, or in some other countries, it's possible to use after the fermentation, direct the material when it is sanitized, direct and use it as a fertilizer on agriculture area. Then you don't need this very energy intensive areas of composting and dewatering. So for countries without winter, where it's possible to use the material as a liquid fertilizer, then it is very important that the fermentation process is able to sanitize the material. Or you have to sanitize the material after the fermentation process by 1 hour by 70 degrees. So this is so-called pasteurization. You have to integrate in the system, but in total much more cheaper than all these areas of post-composting. So effort of treatment before fermentation, wet technology high, dry technology high, dry discontinuity low. And so please read all this this kind of very important aspects and find so at the end the technology which is, what do you think, the best one, and at the end you came to the result dry continuously one or dry discontinuously one. But the main point at the end, I want to do it in a very short time. Fermentation versus composting. Provision of renewable energy, biogas, sure, this is very positive for the fermentation. Higher resources efficiency, sure, you have your fertilizer, you have your organic matter, and you have your biogas. Reduced exhaust air volume, yes, because the fermentation process is totally enclosed or encapsulated. Lower emission loads of greenhouse gases, I'm not sure, because we have some problems with the methane emissions. So at the end, it is not clear that the emission of greenhouse gases from the facility are lower. We can arrange it, but we have to optimize. Lower specific land requirement, more or less this is the case because you don't need so much place for fermentation. Higher investment cost, sure. The investment costs are higher by anaerobic digestion. Higher operational requirements, yes, you have it. it was good, but it depends if you need a post-composting or not. Higher failure susceptibility, yes, you have it with anaerobic digestion. Higher demands on technical stuff. Sorry, the staff must have much more experience with the technology to operate it in a well way. So a very important part is at the end investment cost and operational cost. That means when you don't have a funding system like a law or like a text that the electricity is funded and you get more than on the market, then normally the anaerobic process is not payable. And this development that we start with anaerobic digestion by around 2000, background and precondition was the funding of the gas of the renewable energy. So that's the end.